So the next speaker is going to be Alexei Smolin. Yeah. Still have to wait a bit, I guess. Yes, but it's good.
Thank you.
Yeah, but yes, of course. Let's wait.
Wait. Okay.
Yes, let's wait 2 more minutes now. Otherwise, we're ahead of schedule. That's also not good. Building up the tension. We were getting more and more anxious what you have to do. So I can already announce his title. Alexei will be talking about multiscale model of mechanical behavior of ceramics composites with soft matter filling based on movable cellular automation.
Thank you, okay. Mr. Chairman. I'm from Russia, Tomsk, and I'm from Institute of Strength Physics and Material Science. And I have 2 co-authors. First, my colleague from the same institute, and the third is a master student from Tomsk State University. So I will talk about simulation using particles-based method. So the objective is to present a new multiscale 3D model for simulating mechanical behavior, which means I will describe deformations and fracture of zirconia-based composites with inclusions of soft matter filler. And the simulation based on discrete approach and show the capability of this model and approach. So outline is first objective and motivation. Here I will say a little bit about real materials, then basics and peculiarities of the method of modeling, then about the actual procedure of simulation, multi-scale simulation of such materials, then about the results, and finally I hope I will make some conclusions. Well, we start from objectives and motivations. So we try to model zirconia-based ceramics, which is filled with some soft inclusions. Actually, this originates from medicine. So this ceramic may be used for implants in bone tissues and other, let's say, tissues of the human body. And this filler actually is much softer than the matrix. And a specific feature for these ceramics and this medical application is that this ceramics has a multi-scale structure. Of course, so initially when you produce ceramic, it usually has unimodal distribution of pores, but for medical applications, we you have to use special fillers from organic materials to produce larger pores. So we actually have two parameters for pores, small pores and large pores. And if we try to vary the porosity, of course, for small porosity we have closed pores. With larger porosity we have some clusters of interconnected pores. And for large porosity, actually we have permeable materials. So we try to create the model which allow us to describe this structure of materials, and we try to use the specific features of the filler, as I said. So about the method for modeling, it is so-called movable cellular automaton method. It is based on the discrete approach, which means that we consider material as an ensemble of discrete elements. We call them automata. They have finite size, and they can change their state, position, and orientation in space due to local interaction with neighboring elements. We can also introduce a new type of state. This is the state of the pair of two automata, and controlling parameters of this pair are special. In space is the overlapping parameter and relative rotation. And then we can consider two formalism from cellular automata. Bistable automaton formalism allow us to consider bonded particles and non-bonded particles, and transitions from bonded to unbonded means they actually fracture on this scale. Reverse switching means that this pair can actually the crack can be healed, or some macro welding occurs. If we apply excitable automaton formalism for these parameters, we can actually, based on the Wiener-Rosenbluth model, we can derive from here approach the motion of equations of the system of such element. And final analysis, we have the motion equations in Newton-Euler system. Just Newton equations govern the spatial motion, and Euler equations describe the rotations. And distinguished feature of this approach is that for Newton equations, we explicitly consider so-called volume-dependent force. Actually, this is the many-particle part of the interactions, which is, as I said, specific feature of this approach. And to describe material properties, we use so-called response functions of these automata. Linear response functions allow to describe linear elastic materials. We can also use these curved linear response functions, which allow us to describe the degradation of the material at the scale lower than these particles, and also the plastic behavior of materials. Of course, one of the questions which can occur why we use this, let's say, extraordinary approach, and I think I will just maybe skip 2 slides, and my answer is the following. If you have participated on the conference on particle-based method, which held in Barcelona, usually, and in Germany, and special conference on discrete element methods, maybe you saw one of the motto of such people. They write on these T-shirts, "We love particles." So my answer why I use this approach, because I love particles and I love cellular automata. So, but actually, here it is described how we compute central interaction force and tangential interaction force. But if somebody really interested in this, you can ask me later during this conference or later. Well, the next is actually multiscale simulation technique. And I would say that actually it may be considered not only for this particle-based method, but also for finite element method, I think. So we start from the smallest pore size. We consider, let's say, squared particle specimen and generate pores explicitly. And then we try to simulate uniaxial compression. We get the stress-strain curve. From this strain-strain, I will show this example of such curves later a little bit. So from this curve, we can get elastic models of such a specimen and compression strength. So just elastic modulus is inclinations of the line, and the strength is the highest point. And these two parameters, and we can also get the Poisson ratio. These parameters actually will scatter for different space position of pores. So we have these parameters and parameters of well distributions of them. And this parameter describes the material actually which will be used on next spatial level, let's say called meso level, and this allows us to pass to these large pores. So at this level, we used the parameters that we get at the previous level, and here we explicitly consider large pores or fillers, like in these simulations. So this is actually the procedure of multi-scale approach used for this type of materials. And a little bit in detail. So we start, let's say usual body materials is closed package of these particles, usually in FCC packing, and to get pores, we just remove some particles, so we have randomly selected pores, and we try also to check if these pores interconnected or not, and in final analysis we get this structure, porous structure of this level. And because we use random positions, so we have, let's say, 5 or larger number of small specimens, and we have larger specimens and larger, and try to see the convergence of these obtained elastic modulus, strengths, and so on. Here you can see the example for convergence of elastic modulus. It's rather fast. For strength, a little bit lower, but nevertheless we have convergence. Here you can see the example of stress-strain curves, and you can see that actually elastic modulus is approximately the same, but we have a large scatter of strength. As I said, we try to apply Weibull analysis for this data, which allow us to build the Weibull distribution functions for elastic modulus and for the strength at this scale. On the right, it is just Weibull plots. And here we can see that, say, mesoscale. Well, this sample color means the scatter of the strength. And you can see the results for just different, let's say, realizations of this scatter. And we have also different stress-strain curves. And below is the just desirable plot, and the points are the actually realizations of such specimens. And you can see that the fracture of this specimen is not just like homogeneous material, it is really inhomogeneous material. Well, so as I said, this approach was applied for modeling or simulation of the composite with soft filling. So actually, this soft filling inclusions was of cylindrical shape, and we considered two types of this structure. One is the unidirectional orientation of these cylinders, and the second just a random orientation of these cylinders. And I will just mark this type as, let's say, alpha Y45, and random. So here is the results of these multiscale simulations for elastic modulus and for strength. You can see that the elastic modulus actually has no scatter, and we have a larger scatter for strength. And you can also see that the elastic modulus is actually the same for both structures, but strength is different. And the most interesting result is for Poisson ratio of such specimen. You can see that, let's say, for random position, we have, of course, for random position, we have a smaller, let's say, volume fracture, and it looks like it is descending. And for unidirectional structure, it is approximately the same, but very large scatter. And if you consider just fitting in this small range, it may be considered like increasing. But I have to say that this case of filler has the same Poisson ratio as the base matrix. But if we consider the fillers with Poisson ratio larger, before it was about 0.3, but here on this slide 0.45, it is pronouncedly increasing for both structures. And if we consider the same structure of pores, so with cylindrical pores, which actually means that filler, there is no filler, and its Poisson ratio actually 0. Here you pronouncedly decreasing for both structures. And this allows me to come to conclusions. So first is that we can conclude that a proposed multiscale model based on the MCA method allow us simulating and studying deformation fracture of ceramic composite with elongated soft inclusions. The simulation of, and actually random orientation of elongated soft inclusions results in higher strength value and doesn't change Young's modulus of the model ceramics composite, and the magnitude of Poisson ratio along both lateral directions are approximately the same and keep constant with the Poisson ratio 0.3, and increases with increasing volume for Poisson ratio of inclusions is larger. Thank you very much. I have the last slide, so thank you.